We have an exam tomorrow with magnetism, so we should do some review. Basically, let's start with the first law that we have, the electric field relating to the magnetic field with the speed of light. So it's kind of like the era is BC. Alright, so we're in BC era. Now, let's look at the Lorentz force here, which is pretty important. It's pretty common. F equals QE. We got this field, the electric force, and then we have the Q equals V cross B, which gives us this magnetic force. Now, this magnetic force is perpendicular to the motion, so it's going to change the direction of the charge or the flowing current, but the electric force is going to basically speed up the charge. So they're kind of doing different things. This thing is causing acceleration forward, and then this thing is causing a turning of direction. So it's so that's pretty cool. That's why we're using the curl here. So here's some basic fields based off of electricity. These are some important things to remember as we're going into magnetism. So just remember that we got the electric field at a point, the electric field at a line, and naturally these electric fields are related to the magnetic fields in terms of the flux here. So Faraday's law kind of gives us the change of flux for the magnetic field. And the Faraday induction also gives us this change. But realize that right now we're looking kind of at magnetostatics where we have no change in the magnetic field. So let's put this right here, because the idea is that if we have a constant current, then that means that dJ over dt equals 0 and dB over dt equals 0. We're not getting any kind of magnetic flux or changing of the magnetic field. So this is magnetostatics. Now, we have this Biot-Savart law. That's essentially how we're going to calculate these magnetic fields. And we require these specific currents, like we require the regular current I, or a surface current K, or a volume current J. And with these currents, we can calculate the magnetic field. And the idea is kind of that, here we can zoom in a little bit, we have this strange vortex going on, where the currents are twisting around. And because we have this twisting action, we also have this B field that's just kind of going through it. So it's like a little vortex. And so as the current spins around this little field here, then it also creates this magnetic arrow between it. And this arrow is going to be the same below it as it is above it. And if you stack two of them, then we basically add them two together. We can calculate, it's pretty important to look at this in terms of how to calculate it, because this is probably the most important setup, is if we just have a ring right here. And so since the ring has a current going all the way around it like this, the radius is not changing. So that makes this an easy integral. So what we can do is we kind of have to look at the cross product here of dl cross the r hat, and this curly r is the distance from, the point to the point of charge to the point of measurement, which is equal to r squared plus z squared. And well, if you do a current motion this way and then you cross it upward towards that r hat, then realize that the B field is going to be pointing up here with the thumb pointing sort of off to the perpendicular side here. So that's why we have to look at the cosine component of it, this BZ here, in order to get the field as we go around the entire integral. It all sort of cancels, and the only thing that we have is this vertical field. So the cosine is r divided by this fancy r. And we can shove that into this equation here. And it sort of simplifies into this. The dl is just going to be 2 pi r around the current I here. So it's just like the circumference. And so there we go. It kind of just simplifies this little formula right here. And we can double it to get this. So that's pretty cool. Now, here we have our B's. And here's some basic ones. For example, we can sort of look at Bx for this like infinite wire, or like this wire kind of goes this way. and I guess we can call it infinite, maybe? It doesn't necessarily have to be infinite, but the idea is, again, that we have this current along this wire here. So this is just like a current I. And so, so we basically have a magnetic field that sort of pops out here, and we could use the sign on the left and the sign on the right. We get these two angles here. If we're looking at this point D, where does the field point? I have a feeling that the field points into the page, or it depends on what direction this I is going. So let's just say I is going in that direction. If it's going in that direction, then this B field would be, we have to use the right hand rule, yeah? So put your thumb with the direction of the current, and the magnetic field comes out of the page. So we'll just say like B comes out like this. It comes out specifically at this point right here. So, you know, but we have our two angles that I kind of wanted to put in there. Angle 1, or angle 2 and angle 1 right here. Okay, but then this B field that pops out, I guess we could make it orange because it's important to have the orange field there. Boom. Alright, so that orange field is coming out of the page at that point. Just like that. Boom. Okay, cool. And so, you know, we can do mu naught I over 4 pi d, and then we kind of have to multiply it by the signs of, depending on whether you want to cut it short or have it infinite both directions, and you kind of go up to like pi over 2 for the angles. So an arc segment is similar, but we're using an angle here, which is multiplying it by the angle of the arc segment. And for the loop, this is an Ampérian loop. And this is probably really important law. It comes from here. We take an integral around a loop. We take an integral around a loop, and we want to know where the magnetic field is around a loop. I kind of forgot exactly how that works. But I do have another page on magnetism, so let's go and check that out real quick. So it would be kind of like this one. I might explain this Ampérian loop a little bit better. Oh, yeah, okay, so the idea is that we're looking at it from different angles, because here we're kind of seeing the current as it goes this way horizontally, and we're getting the B field popping out of the page. But what if we were looking at, for example, if the I was popping out of the page here, like this, okay, and the question is, where is the B field curling around it in this direction? Because that's exactly what the picture right above is trying to say. So we can look at it in two different ways. We can look at it from the front, we could look at it from the side, from below, you know, whatever. But we're getting the idea that we have a current coming this way, and the B field is curling around it. And so obviously this is at some kind of a radius, and we'll call it radius r naught, because we have a little an Ampérian loop that goes around it. I guess I'll make it in gray. So the loop is the entire circle that goes around here. Good enough, I guess. It's such a bad arrow right there. I'll try. Let's get this arrow looking good. Okay, so there's our Ampérian loop, and we're at this radius r right here. Or not. So that kind of tells us what the magnetic field is at that point of that loop. So we're just looking at the magnetic field from different directions and seeing how that works. Close this, reopen it. Alright, so let's look at the vector potential, because the potentials are kind of similar to like voltage. Voltage and the vector potential essentially do the same thing. Remember the Laplace equation, which says that the second derivative of the voltage equals some charge density over epsilon naught, or you could say it equals mu naught j. So we're looking at the second derivative of A, the vector potential, being equal to negative mu naught j. This kind of comes from doing this business where we're doing del cross B. We're plugging in the vector potential, so like del cross A into the del cross B. And when we do that, we get this, which becomes an expanded term here. And if A equals, if del dot A equals 0, then this goes away, and we're just left with this, which is sort of a Poisson type equation. And so we kind of get the same general idea using the vector potential as we did from the voltage. And so that means that they're continuous at particular points. And we have some different integrals that we can solve for that, which is very similar to the magnetic field one. We have the I, we have the K, and we have the J. So these equations here kind of have to memorize. I mean, there's really not much to it. There's not really much else we can do about it. Mu naught I over 4 pi dl cross this r hat over r squared. When we go to this thing, it's like mu naught over 4 pi k, and then r hat over r squared dA. And we have dV. We have to cross it. How are we going to remember this? I don't know. The flashcards or something. Now, for the B versus E boundary conditions, we have them sort of opposite. The perpendicular versions are equal for the B terms, and the parallel versions are equal for the electric terms. But then we have this Maxwell type boundary. We do E out minus E in, and we get this free plus the bound charges over epsilon naught. That's perpendicular. For the parallel ones, we get this type of K cross N. Alright. Here's a quick step over the continuity equation and steady state versus the regular continuity. It's pretty simple stuff. We're going to take a look at that. Of course, there's other ways that you can apply the continuity equation in different terms, but we're going to do that a little bit later. For now, we're almost done. Let's just realize we might have to take a look at these magnetic dipole moments, the magnetic moments and the magnetic dipoles. Well, first let's recall how to switch between the currents. We were just talking about the three different types of currents. We have I, K, and J, and they're essentially just time derivative Q. And over here we're taking a circumference derivative, really, a circular dl derivative about this I. And then here we're taking an area derivative of this, or an area derivative of the I. So length derivative versus an area derivative. And of course, it's a little easier if you think of it in terms of the charge density times velocity. Boom, boom, boom. Then you kind of get the same form in all three shapes, which is nice. Here's a couple of important cross products to remember, but we kind of apply it to various shapes. So here's the charge density of a disk, charge density of a shell. these equations should make sense. Here's the charge density of a cylinder and a sphere. That's for the electric stuff. But it goes into our magnetics because, I mean, we need these I, J, and K in order to get currents out of them. So like the charges sort of with the velocities spawn these currents out, and then we have these magnetic moments that kind of pop out of it. Notice here we again have a current I, and we're using an area A. So once you have a current with an area and some n number of loops around it, like a little coil, you get a magnetic moment. And this is mu I, this is mu K, mu J. You can calculate them, I guess. It's kind of annoying, but hey, you know. Yeah, it's a lot easier to do it with the single line here. But if we do it in the second, in the area version, then we have to do R cross dA, or R cross the volume element here. I mean, I don't know, that's a volume element. Anyway, over here we have the magnetic moments for a ring, a disc, cylinder, shell, and sphere. And if we look at it in terms of for the ring, well, the current is kind of like it's kind of like Q divided by T, right? But T is just this. And so we kind of get Q over T becomes this. So that's the current, I. I'll sort of put that right here in blue. So this is the current. Let's zoom in a little bit here. It's the current I. And then this is the area pi r squared. Alright. And so that kind of simplifies down and we get this type of thing. This is for a ring. And then we got all these other ones, which are basically the same, like it's QR squared here. C. QWR squared is the final shape. But we've got some different constants in front of them. So they're all QWR squared. And the key is that we have like a fourth for the disk and the cylinder, a third for the shell, a fifth for the sphere. These coefficients in front come from doing the same type of thing where we take the current and then we multiply it by either the area or the volume. And then we get different coefficients. But you know, if you could just remember the coefficient in front and the QWR squared shape, then that's pretty fine. Now this relates to magnetism, the magnetization, which takes the I wonder if I could do this in brown here. I'm going to do it in brown because I wanted magnetization to be purple. This thing can be brown. So there we go. It's cool I could use this color because it's somewhat rare. Boom. But it kind of fits with the orange stuff. So we'll go like that. And then over here we've got the magnetization, which becomes the magnetic moment divided by the volume. And we can apply that for a cylinder, a shell, or a sphere. Again, we kind of have this coefficient in front. But this all comes from solving this. So once we have the magnetization, you kind of want to be solving for the bound current densities. So you get this stuff here. So imagine this kind of like a wall of charge. This is like a little segment over here that has like kind of a surface of charge. It's not a charge of current. A surface current right here. So there's a surface current going in the same direction as both sides. Doesn't really matter which way, but what we have to do is we have to cross the magnetization, which is coming out of the page here. Cross that with the N hat direction. N hat. And when you do that, so you can basically take out of the page, crossing it with the R hat. R hat, and then you'll get pointing straight up. So it comes out this way, cross, and then you can see that my thumb points straight up. I mean, I guess it depends whether you want to put it the plus or minus, however the current goes. But if you go with the minus hat, oh yeah, this is a minus R hat. So yeah, so anyway, so surface current, the magnetization cross with the negative R hat, and then the Z cross R gives the Jesus Christ. So the reason why magnetism is so much harder than electricity is because of all these cross products. So it's so hard to keep track of which direction you're twisting it. But since this is in the theta hat direction, if we want to cross in the R hat direction, boom, boom, that thing should be pointing down. I don't know why this is positive and negative here. I think I might have mixed up these particular sides here. Double check this, because if I'm crossing it with the positive R hat, and you get a negative Z hat, right? So I think I was just getting myself mixed up here. Yeah, that's why it's so hard. But I think this is more correct here. Anyway, so we kind of have to deal with this. I was doing this like for an hour last night or two. And then you can find I from that. I equals K dl. The dl here is actually along the dz. And so that would equal MA. Oh my god. So this stuff is crazy, but this is indeed how we can calculate this stuff. I didn't really do it for J. Okay, and then we have this idea. That the integral of H, the auxiliary field, man, I could maybe call it like dark red or something. The auxiliary field here is equal to the magnetic field minus the magnetization. So it kind of shifts stuff around. Magnetization just kind of shifts the B field a little bit. It's kind of as if it was like a displacement field. Alright. So that's pretty good there. We got these dipoles we might have to worry about, but I'm not too sure whether the dipoles are going to be part of this exam here. So I think we're pretty much good there. Just remember the Maxwell equations. Just review these real quick here at the end. Differential form right here is interesting, but it's more interesting to look at it in terms of the integral form, because if you see right here, we can see how basically we have like these areas. Like if you have like a sphere, basically the idea is that there's like a charge that sources these fields, and it kind of points outward. around an area, like a surface area. And but if you do that with the magnetic field, it doesn't really work, because the fields come back in. So it's good to kind of draw this. Here we have like a charge. We'll make it a positive charge. Oh my gosh, wrong color. So we have a positive charge, and the fields point outward. And that's basically all that we get. Okay, but with the magnets, they always come in sort of this up and down type of thing where the field lines come back. How can I do this here? The field lines here, they just come back. So, if you were to draw a sphere around here, how can we draw a sphere in there? Like if we draw a sphere here, you can see that all the arrows point out of the sphere, but here, these arrows that point out right here come right back in on the other side. So that's why this stuff equals 0. This, I don't know how you do this, but maybe like that. And we can keep drawing these little arrows around. So boom, that kind of shows us what these integrals are telling us. Now it'd be cool to do it for this stuff here, but let's think about it more like if we have a electric field going in a circle like this, then it generates this kind of stuff. Because look, it generates a flux. Boom. So like, this stuff starts popping out. Kind of starts coming out of the page like that, right? So if we do it like this, it would come out like that. Boom. So like this curling electric field creates it's important to note that the electric field has to change. So like, notice this is the changing in time of this. So I'm going to have to draw like bigger and bigger arrows, because the electric field really has to like change as it's going through this loop here. Okay, and then I believe that the same thing would happen on the other side. What this is telling us is that, again, if we have a current, notice there's no delta T here, so there's no changing. It will literally just create fields on both sides of this current, like this. And that was Ampere's law. So like this side is pretty simple right here. There's our I. We put a field here, and you know, we have our little Ampere's loop around here. But then this part is telling us that kind of the opposite of what this is saying, right? So we have some kind of a curling electric field or magnetic field that's kind of going around. It's due to the change of this electric field. So how does this work? I'm pretty sure that if we start amplifying this field here, this current, I think this creates an opposite field here. In the other direction, because notice how this one, if we started amplifying it, oops, it spun the regular way. Hopefully I'm doing this correctly. But this one, if we amplify it, usually the magnetic field wants to like reverse its effect. And I'm wondering whether that was this particular one, or whether it was this particular one. Can't remember right now, but the idea is that, again, we're going to have this curling action around it. This field comes out due to the change of the flux there. Because I mean, this is fluxing. And so it should produce a magnetic field. I don't know. These ones are a little bit harder to interpret than these ones. And I do think that this is the correct way to look at it. You can also double check by sort of reviewing this thing one more time. Sort of drew it a little bit better here. Yeah, so this one is actually the opposite effect here. I think that was my instinct is telling, because look at this minus sign here. See, so it's kind of the opposite of the right-hand rule. So we have to spin this current the other way if we're amplifying that B field. You know, so if the B field is amplifying, this thing is going to go the opposite direction and flow into the page up here and out of the page down there. Whereas here we have the right-hand rule as normal with the Ampere's law, and then and then the capacitor plate changing is a little bit better. Yeah, there's like a B field that starts to form inside of there. Okay, yeah. But I'm pretty sure it's the right-hand rule for that one. Okay, so we're good now. This one's a regular old increasing field. We should use the right-hand rule for this one, and this one is the opposite. Anyway, so there we go. We've kind of reviewed these little bits here, and I think that's pretty much it for this video. Let's go ahead and call it a day. Thank you so much for watching. Hopefully